So again, I forgot I wasn't recording. So if the problem says for you to find grams, don't be thinking about grams, be thinking of moles. So this equation is number of moles here. You can use molar mass to convert grams to moles or moles to grams. But the purpose of today is we're going to do some mole conversion. And if I have time, I'll go over some more combined gas law stuff. So, mole conversion practice. So, at STP, 1 mole of a gas takes up a volume of 22.4 liters. So at STP, 1 mole of a gas takes up a volume of 22.4 liters. So in other words, at STP, 22.4. 1 mole equals 6.022 times 10 to the 23 particles equals 22.4 liters. We have conversion factors between moles, particles, and liters. If your temperature is 0 degrees Celsius or 273.15 Kelvin, and your pressure is equal to 1 atmosphere or 101.325 kilopascals. If this is true, and this is true, if you had 6.022 times 10 to the 23 particles, i.e. a mole of a gas, it will take up a volume of 22.4 liters. So let's assume everything's at STP. How many moles are in a 5-liter tank of helium? How many moles are in a 5-liter tank of helium? Well, this is just a dimensional analysis problem. We start with 5 liters. We know that if we're at STP, we have a ratio of 1 mole to 22.4 liters. We have liter on top, so we need to put liter on bottom and mole on top. We know it is 22.4 to 1 mole. Would someone close the door, please? And that is equal to 0.223214 mole. By the way, did I tell y'all about the homework to be putting 4 or 5 significant figures? Yes. Okay, just making sure. So for all homework for the rest of the class, make sure you at least put 4 or 5 digits. I've basically abandoned significant figures. Also, on any homework, if the homework says use significant figures, ignore it. I only teach significant figures at the beginning because it's important to know, to be introduced to it. But I really hate it. I prefer the notation of 0.5 plus or minus 0.1. What this tells you is that the answer is somewhere between 0.4 and 0.6. And this is too complicated for you guys to analyze the round, so I just ignore significant figure. Y'all were taught it. Y'all seem to have gotten it at one point. That's good enough. Alright, let's do another problem. How many grams are in a 2-liter? How many grams of O2 are in a 2-liter bottle? Assuming the bottle is just filled with O2. So how many grams of O2 are in a 2-liter bottle containing just O2? Be more accurate. Containing only O2. Again, if it doesn't specify, so assume STP. So, again, this was a very good point you made, Lucas. How do you get grams? You usually can't directly solve for grams in this class. What you can do is solve for moles. And then you can use the periodic table to convert moles into grams. So let's solve for moles first. We have 2 liters. And we know that if we're at STP, 22.4 liters is equal to 1 mole. Standard temperature and pressure. If you're at STP, yes, it's 22.4. If you're not at STP, meaning if you increase the temperature, volume increases. If you decrease the pressure, volume decreases. If you're at STP. I'll tell you when you're at STP. Yes, every gas at STP has the exact same volume. It doesn't matter what gas. So if you had water vapor, if it's at STP, and it doesn't really quite work. Why can't you really work with water vapor? So what is water a gas at 0 degrees Celsius? It would freeze. It would turn solid. So it's not a gas. But what we can do is pretend like it's a gas. We'll see later on when we get more advanced with this. We can pretend it stays a gas and do some factors with this. This is more of a useful tool. I mean, this is true. If for example oxygen stays a gas at 0 degrees versus hydrogen, what we can do is we can temporarily change gases into STP and figure out volume for it based on some information. So this is just a neat tool. It's just a fact that at STP, regardless of the gas, it will take up 1 mole will take up exactly 22.4 liters. It's just a property of gases. The reason why this is true is because of kinetic molecular theory, KMT. We assume that all the molecules are super small and their size don't matter. It doesn't matter if we have an O2, an H2O, some much larger molecule. We assume that they're so tiny their size don't matter. Basically, all particles are identical when it's in gas form. Their size really doesn't matter. The only exception to this is temperature, because temperature is based on average kinetic energy, and even though their sizes we treat them to be the same, the mass changes, and 1/2 mv squared means that it's going to change. But anyway, how many grams of O2 are in a 2-liter bottle containing only O2? So we can convert this 2 liters into liters. So liter is going to cancel out. We're now in moles. And we can convert these liters into moles. From moles, we can look at our fancy periodic table. O2 is just 2. So it is 31.9988 grams per mole. Oxygen is going to be something you'll memorize. So yeah, we want moles to cancel out, so we put mole here, gram here. So it'd be 31.9988 grams for whatever 1 mole. Moles cancel out, we're now in grams. So 2.857037 grams. So as I said, grams to moles. It's gonna be sneaky. It's gonna be always there. You're gonna be using it for most. Yeah, if it asks for grams, you have to use molar mass to convert moles into grams. No, on that packet, you don't use this. Yeah, that one you use ideal gas law. You use this equation, and you get number of moles. Alright. Let's say we wanted to go in reverse. So how many liters does 5 grams of O2 take up at STP? So we're given grams, but we can't use grams directly. We have to use moles. So let's first convert grams into moles. We know that it's 31.9988 grams for every 1 mole. So grams cancel out. And now we can add the conversion factor of 1 mole to 22.4 liters. Which tells us that it's a 3.50013, and this would be liters. I'm about to. No. Alright, let's do what volume would 5 times 10 to the 23 particles of O2 take up? And again, at STP. So again, dimensional analysis. 5 times 10 to the 23 particles. What would be our next conversion factor? Yes. Yeah, so this is the conversion factor between particles and moles, or atoms to moles, or molecules to moles. We use Avogadro's number. So this is how we convert between that. So particles disappear, and we're now in moles. And now we can convert moles into liters using the fact that 1 mole of a gas at STP takes up a volume of 22.4 liters. By the way, this definition of 22.4 liters has changed, I think. Because STP has changed. Our standard temperature and pressure has changed very slightly. But in this class, it doesn't matter where we use these values. Just note that this is only true before the 70s. So, what was standard pressure? 1 atmosphere, and 1 atmosphere in kilopascals. So, let me look that up. See if I'm right. So, standard STP. So I don't get confused or confuse you guys. We're going to assume what I teach, because this is, let's see, standard conditions for temperature and pressure. Until 1982, STP was defined as a temperature of 0 degrees Celsius and a pressure of 1 atmosphere, or 101.325 kilopascals. Note that they wanted to be more metric. Kilopascal is more metric. So after 1982, the standard temperature and pressure was defined as exactly 100 kilopascals. So we're using pre-1982 definition of standard STP. Note that it's just 1.325 kilopascals off. The numbers are going to be about the same. Because in this class, 1 atmosphere is the pressure of a room. 100 kilopascal is slightly below atmospheric pressure. And on a high school level, it's easier to teach students atmospheres because atmospheres are easier to work with. In college chemistry, they will tell you it's equal to 10 to the 5th pascals. They work in pascals. Or you can condense that into kilopascals. Yes, 1 bar is equal to 10 to the 5th pascals. It stands for, what does it stand for? They're on the screen. I'm assuming that. Oh, it's the pressure of literally it's the pressure of 700 bar flattened this length. I don't know. I don't. I forget. But anyway, my point was: that do note that we're using a slightly outdated thing, and it's because in high school we usually do atmospheres and not. And put your mask back on, Tristan. So anyway, once you did this, so moles would now cancel out with moles, and we're left with just liters. I think it's 22.6 if you use the current definition. But again, we're not going to be using the current definition. I try to work with atmospheres. And it makes math easier if we just stick with the previous atmosphere definition. I think technically, no, it wasn't on. Then you type. You need to put parentheses around this number in the denominator. By the way, it's a good thing to be typing these numbers into the calculator, because I do not know how many times I see on test someone type in this answer, 1.859847 times 10 to the 47 liters, and think, that's what the calculator said. It has to be right. Yes, that's what you should do, is know it's wrong. Because what you typed in 5 times 10 to the 23 times 22.4 divided by 6.022. Because you didn't put parentheses around it, you then multiplied it by 10 to the 23. You should, to put this on the denominator, you need to tell calculator it's connected. It doesn't matter if it's on top. And keep your mask on. If it's on the bottom. What's your question? You could also use E and don't have to worry about parentheses. Yeah, I guess. Alright, so everyone's good with that? Let's look over ideal gas law in more detail. So, PV equal to nRT. How many grams of O2 will occupy a volume of 2,500 milliliters at a pressure of 1.2 atmospheres and temperature of 20 degrees Celsius. So how many grams of O2 will occupy a volume of 2,500 milliliters at a pressure of 1.2 atmospheres and temperature of 20 degrees Celsius. Our R values is 0.0821 liter atmosphere per mole Kelvin. This was just given. They're constants, they never change. It's this R right here. It's just constants. It's a constant, like pi is equal to 3.1415. My door's always locked. Alright, so how many grams of O2 will occupy a volume of 2,500 milliliters at a pressure of 1.2 atmospheres? Let's make it even. Raise that, make it 1.5. 1.5 atmospheres. And a temperature of 20 degrees Celsius. So we're solving for grams. And this is our equation. Again, if you know moles, you know grams. So basically we need to solve for number of moles first. N would be equal to pressure times volume over the constant RT, or R times temperature. Which of these R's will we use? The first, the middle, or the third? Which of these R values should we use in this equation? Yes. So since we're given a pressure in atmospheres, we need to use this one because it's in atmospheres. So our pressure is 1.5 atmospheres, and thus we should use an R value of 0.0821 liter atmospheres per mole Kelvin. Our volume is 2,500 milliliters. But note, this has a liter in its units. How many liters is 2,500 milliliters? It'd be 2.5. So this is equal to 2.5 liters. And then we have a temperature of 20 degrees Celsius. And you're correct, we can't keep in Celsius, we have to go into Kelvin. That's 293.15 Kelvin. Now we can just plug all these numbers in. Our pressure is 1.5 atmospheres. Times a volume, we need to use liters. And we use the R value 0.0821 liters times atmospheres divided by mole Kelvin. And then we have a temperature of 293.15 Kelvin. Before continuing, let's look at the units. Let's do a little bit of a dimensional analysis. A Kelvin divided by a Kelvin cancel each other out. We have an atmosphere divided by an atmosphere. That cancels each other out. A liter divided by a liter cancel each other out. And we're left with a divided by mole on the bottom. We take the reciprocal, and it gives us a mole on top. So our answer is going to be moles. That is what our equation is solving for, so we're good. The units agree that wherever these numbers should be comes out to be in moles. So if you use this equation, we use R because there's an R in the equation. So in this one, we're trying to solve for grams. The only equation that deals with moles or grams is this one. So the problem doesn't deal with moles or grams. You don't use this equation. Oh, because our pressure is in atmospheres. So we look at the pressure units. Atmospheres, kilopascals, and millimeters mercury. These only differ by what pressure unit we're in. It's liters times pressure divided by mole Kelvin. So if it uses the pressure of atmospheres, note that if you can use the other ones. You can use the other ones, but we'd have to convert the pressure into whatever unit. Yes, exactly. I think on the test, though, we'll do some more examples later. But on the test, I might give you only one R value, and you'd have to convert the pressure. So this tells us the moles. So we're currently in moles, but the question asked about grams. So we need to convert mole into grams. We know that 1 mole of O2 is equal to 31.9988 grams. That's 4.985766. Moles cancel out. Our only unit is grams. So almost 5 grams. Another thing that tells you which R you should use is if I were to, I said you have 5 grams of O2, find at what pressure and atmospheres of pressure, then you would have to use the R that uses atmospheres. Or if I said find in millimeters mercury, the pressure, then you'd have to use this one. Or you can do conversion factors between them. So, for example, so let's look at this. R equals 0.0821 liter times atmosphere per 1 mole. So we have, so let's look at the R value. R value 0.0821 liter times atmosphere over mole Kelvin. So this value is 0.0821 liters times 1 atmosphere divided by 1 mole and 1 Kelvin. So I broke this up into a grid. This number right here is the same thing as this grid right here, right? We have a liter times the atmosphere divided by mole divided by Kelvin. These units are all broken up like this. If I wanted to convert it into kilopascals, 1 atmosphere is equal to 101.325 kilopascals. So atmospheres cancel out. And if I rework this problem, I get this is equal to 8.3187825. My units that are left are liters times kilopascals divided by mole Kelvin. And if we look back our R values, that's this R value right here. 8.31. 8.31. Note again, they're slightly off. Technically 8.31 would round up to 8.32, but use whatever values given to you. But you can convert between different R values by doing dimensional analysis on the dimensions of the units. I wanted to replace the atmosphere with kilopascal, so I broke them all up and did some conversion. My units are liters times kilopascals divided by moles divided by Kelvin. You come over here and make that. Some more advanced dimensional analysis. So is everyone good on ideal gas law? So for remote learners, here's the code word. So here's more homework. What we did today. It's two. There's a front and back. And let me grab the other homework, the giant packet. Where is it? I got it somewhere around here. Ah, here it is. We'll do this one together. So this is duplicated again on the left and right side. What now? Oh, assume on the homework, by the way, on the homework, assume all these problems are at STP. And it basically tells you here, assume 1 mole is 22.4 liters. Yes, so you start it with moles, and here's your conversion factor. Dimensional analysis. This entire paper right here is pure dimensional analysis. This is your conversion factors. You just plug in your conversion factors, converting moles into whatever. Yeah, this one's simplified. Here, it just basically tells you this is what your number you start with. Use dimensional analysis. So anything not turned in after Friday is going to be an automatic 0. Any test not corrected by Friday is also. So Friday's the end of the 6 weeks. It's not due tomorrow. It's probably due the next day after, Thursday. So let's do, I'm doing the right side because it looks better. So again, you don't need to worry about significant figures. I want decimals least 4 or 5 significant figures. So a oxygen gas occupies a volume of 250 liters at 740 atmospheres of pressure. What volume will occupy at 800 atmospheres pressure? Again, on these questions, ignore significant figures. For the rest of the entire year, I want at least 4 or 5, regardless of the problem. So, here we're only dealing with volume and pressure. So this is going to be a PV equals PV problem. There's no temperature involved. So we have this is our initial volume, initial pressure, and this would be our final pressure. So we're solving for V2, or final volume. So V2, using some algebra, should be equal to P1 V1 over P2. Our initial pressure is 740 atmospheres times our initial volume of 250 liters divided by our final. And you get 231.25. Atmospheres cancel out, so this problem's in liters. Again, for combined gas law, this is what we're working with. That will be our equation. If it doesn't refer to one variable, we can remove it from the problem. And also, we use 0.15. So a volume of neon gas at 75 atmospheres changed from 75 liters to 125 liters. What would be the new pressure? So this is initial pressure. This is initial volume. And this is the new volume. So we're solving for P2. So P1, V1, we don't deal with temperature. So when writing this equation down, we can omit temperature. And we're solving for P2. P2 is thus equal to P1, V1 over V2. Again, when doing this math, it's very important that you include units and actually check that the units cancel out. So pressure 1 is 75 atmospheres. Volume 1 is 75 liters. And 125 liters for volume 2. Check to see if the units cancel out. So liters and liters gives us atmospheres. Atmospheres is unit pressure, so we're good. And that gives us 45 atmospheres. And we're almost out of time. So that's basically what we do for all the combined gas law. Yes, the packet is almost entirely this.
That easy?
It's always been that easy. There are about 3 or 4, maybe 5 questions tops that are more difficult. 15. So the first 2 problems is just add 273.15. Then we have like 13 problems that are this easy. So yes. So when volume increases, pressure decreases. The more thought of doing this is imagine if we took all the air in this room and shrunk it down in that corner. It would be at extremely high pressure in that corner, right? And when we let it fill back up the room, it will decrease in pressure. It's more you more think of it because you really can't change pressure. What you more can change is the volume. So you're changing volume, and that's causing the pressure to drop. Write your name on board. Or you could take the calculator and tilt your phone to the side. That's it for today.